Okay, this is a video lesson for Unit 4, Lesson 1, which is uniform distributions. This unit is about something called normal distributions, which we've talked a little bit about, but we're going to dive way deeper into in this unit. So we're going to go after uniform first because uniform is kind of the easiest version of a continuous distribution. And normal distributions are also continuous, but they're a little bit more complicated. So it's a lot easier to understand what's going on by dealing with uniform first, even though it's a little bit less important. But what you're going to learn in this lesson is really important in terms of building the skills that you'll need for when we get to the big stuff in normal distributions. So last chapter, what we dealt with was called a discrete probability function. That's when it was easy to find the probability of something like one successful coin flip out of five. What's the probability of getting one heads out of five? Where this unit is about continuous distributions. Now, continuous is a little bit more complicated, and we're going to talk about that more as the unit goes on. But continuous would be something like how much water is in a water bottle. The probability of exactly 16 ounces is actually really tiny because you're not counting 16.0001 ounces. You're not counting 15.9 ounces. You're only counting 16. So when the data can be continuous and there's not really countable numbers, that's when it becomes a little bit harder to calculate the probability. So instead of finding the probability of a specific number like 16 ounces, instead we're going to care about ranges. Like what's the probability that there's anywhere between 15 and 16 ounces of water in the water bottle? And that's more realistic to figure out. It's not easier to figure out, but it is more realistic, and you're going to get a real probability there. It's much different to do this, to find continuous probability distributions. It's much different, and we have to use this trick of counting probability as an area. What we're going to do is eventually we're going to learn the normal distribution, and we're going to look at shapes, the normal distribution shape, and we're going to use that to calculate probability, and you'll learn that soon enough. What using area for probability is we're going to create something called a density curve, and there's a few rules about a density curve. The total area under the curve has to equal 1. That's one of the rules. Every point has a height of 0 or greater. What this does is it simulates probability. All probability is supposed to add up to 1. So if the area under the curve adds up to 1, that kind of acts like probability. The heights act like individual probabilities. Any individual probability has to be greater than 0, and that's why this says the height is 0 or greater. So the shape acts like probability does, which is kind of a weird concept, but it's really effective for us in calculating probabilities. So once we use this information, we can actually calculate area and have it represent a probability, and we can solve probability problems using shapes, which is a really crazy new concept for us. So the distribution we're going to talk about today is called the uniform distribution. You will kind of recognize it as the rectangle distribution. You see the shape that we're getting out of a uniform distribution is a rectangle. And what you're going to see there is all of the individual probabilities, anywhere from like 4 to 12 for this shape. They all have the exact same probability of occurring. They all have the same height. So the height over here, the y-axis, serves as the probability. And x, the x-axis, is just like the x's we had in discrete, where this represents 0 of whatever we're doing, 2 of whatever we're doing, 4 of whatever we're doing. Last chapter is usually about occurrences or successes, but we also had random variables that represented things like, profit or losses. So whatever x is representing goes on the x-axis, and the probabilities go on the y-axis. And we're going to get this flat shape that's going to create a rectangle. So A random variable has a uniform distribution between 3 and 13, and they're going to ask us to find these probabilities. So what we're going to do is we're going to draw some axes. You want to draw the shape here. The shape is critical. So we're going to draw the shape. We're going to start off by axes. This is the x-axis, and we know that all of the random variable has a uniform distribution between 3 and 13. So we know the x-axis is going to go from 3 to 13, and we want to label that. We don't know how tall the rectangle is going to be, but when they say uniform, that means rectangle. So I'm going to draw a rectangle from 3 to 13. I don't know, however, how tall it's supposed to be. What I do know is it is bounded, or the area is 1. And we know that the length times width of a rectangle equals area. Area equals length times width. Well, I actually know the length. The length of this rectangle, or sorry, the width of this rectangle is from 3 to 13, which is 10 units wide. So I know my width is 10. Whatever the length or the height, whatever you want to call it here, whatever the height of this rectangle is, that's supposed to be the probability. But oh wait, I also know that area equals 1. So I have area equals length times width. Area equals length times 10. If I want to solve for the length, I could divide by 10. And that gives me an answer of the height, or the length, whatever you want to call it here, equaling 1/10. That is this height right here, which 1/10 also equals 0.1. So now I know the height is 0.1. I know the width is 10. Well, this is actually huge because this is the probability of x for all those individual x's. So the height matters here. It's really important. Okay? And like I said, the area is 1. So now, when we're asked a question like what's the probability that x, and by the way, I'm going to make this really a lot smaller here so I have some room to draw some of the other pictures. Okay? When they say what's the probability that x is greater than 10, well, what we're looking at is from 10. I guess I'm actually going to use this picture here. Okay, we're going to get rid of this label that it says area equals 1. The height, or the x here, they want x is greater than 10. So wherever 10 is, we're going to draw that. And what they're asking is, what's this chunk of the rectangle? What's that size? Well, the probability equals the area. That's the whole thing with this unit, is the area from 10 to whatever the cap is, which in this case is 13. The area is the probability. So we want to find the area from 10 to 13. So we have a base here of 3 and a height here of still 0.1. So if we take 3 times 0.1, the base times the height, we will get the probability, which is the area. So I go to my calculator if you need to. 3 times 0.1 equals 0.3. And that's our answer there. So what we're doing is we are finding the area that goes with the statement. So now, let me go ahead and redraw this one for a probability of less than 8. Okay? The picture we were dealing with was from 3 to 13. We figured out, and this was the most important part of the problem, we figured out that the height was 0.1 at the beginning. We figured it out by drawing the picture and using the area formula to calculate the height. So now they want less than 8. So I'm going to find 8. somewhere on the number line. I still know from that first part that I did that the height is 0.1. There's 8, and they want less than 8, which is really this chunk of the rectangle. This chunk has a base of 3 to 8, which is 5. 5 units wide. 8 minus 3 equals 5. So that's my base. My height is always the same for a uniform. My height's 0.1. So this probability is going to equal base 5 times height 0.1, which equals 0.5. And that'll be our answer. Whatever the area is that goes according to the interval we were finding, that is equal to the probability. That's how density curves work. That's how uniform distributions work. So one more picture here. I'll cheat a little bit and copy and paste this picture to do it. So this time they want to know about 7 to 12. Here's 7 somewhere around here. Here's 12 somewhere around here. They want to know what's the probability that x is between 7 and 12. So what's the probability that x is in this little rectangle? Well, base times height. We're just finding the area of rectangles. That's really all we're doing. From 7 to 12 is 5 units wide, or a base of 5, and the height is always 0.1. So again, I'm doing 5 times 0.1, which equals 0.5. And that's that probability. So let's try this again here in this next example. Ace Heating and Air Conditioning Services finds that the amount of time a repairman needs to fix a furnace is uniformly distributed between 1 and 5 hours. So uniform, as soon as you see this word, uniformly distributed, you're thinking rectangle. So I'm going to draw my rectangle by setting up my base, or my axes first. Okay, I'm going to put 1 to 5. That's where we're spreading out from. From 1 to 5 is where the rectangle is going to be. I'm drawing that right now. I don't know the height. I'm typically not going to know the height at the beginning of the problem, but that is something that we can figure out. Okay? We know that for the big shape, the big rectangle, the area equals 1. We know that area equals, this time I'm going to call it base times height. That's more typically what I call it. Base times height. Okay? We know that area equals 1. So I can replace A with 1. The base here is from 1 to 5, which is 4 units wide. So my base is 4, and what I really want to know is my height. If I knew my height, then I would know my probability. So I'm going to divide both sides by 4, and I get 1 divided by 4, or 0.25, is the height. So right here, we're going to put 0.25. That's our height. I'm going to get rid of this little note that the area equals 1, and I'm going to take this little calculation and shrink it up and get it out of the way so I have room to do this problem. Okay, but this was the key, was finding this number. That I had to go do. It takes a little bit of math to go figure it out. Now that I know that number, I'm going to kind of get rid of all this stuff because I don't need any of this information now that I have that number. Now, what's the question really asking? Find the probability that it takes more than 3.5 hours. So x is greater than 3.5. So I'm going to find 3.5 on the number line. You don't have to be super accurate here. Just draw it somewhere in between 1 and 5. And I want more than that. So what I'm looking for here is the area of that rectangle. Well, the area of a rectangle is base times height. My base here is 5 minus 3.5, which is 1.5. and we already figured out the height. The height is 0.25. And now this is something I can type in my calculator. 1.5 times 0.25. That gives me an answer of 0.375, which is our probability. And we've got one more problem to do. Same idea. This is the point in the video where I would probably pause it, try this one on your own, and see if you got it right. So I'm going to go a little faster. I'm going to draw the picture. I'm uniformly distributed from 123 to 125, so 123 to 125. I always draw my rectangle with a uniform. So there's my rectangle. Okay, the area underneath is 1. So 1, the area of the rectangle, it's always 1, equals base times height. My base is 2 units wide, so 2 times, I don't know the height. I divide by 2, and I get h equals 0.5. 1 divided by 2 equals 0.5. So right here is 0.5. That's my consistent height. That's what a uniform distribution is. It's something where all of the random variable range all has the same probability of occurring, and that height's 0.5. So now they ask us to find the probability that it is greater than 124.5. Okay, well, I'm going to go find 124.5. And I'm going to draw that little rectangle. And that's the shape I'm going to find the area of. The height here is 0.5. The width here is just going from 124.5 to 125, so it's 1/2, 0.5. So I have a height of 0.5 and a base of 0.5. So base times height would be 0.5 times 0.5, giving us an answer of 0.25, which is our final answer. So it's weird. This is a whole new world of math for you to be using shapes to find probabilities. But this is kind of what we're going to be in for the next several units. So hopefully you understood this, because this is really going to set you up to understand normal distributions, which we'll go really, really far with. And that's it for this lesson.